Okay, in this example, we have a circuit, simple circuit. Two capacitors are connected in series and two resistors, okay? And the values of the capacitors are 6 microfarad, and the values of these two resistors are 2.2 kilo ohms, and the power supply is 12 volts, and there is a switch there, okay? And the current is supposed to flow this way initially, but you know that actually the current is not flowing here. As the current is going, this plus signs are here, okay? All of a sudden, this other side of the capacitor plate will have to be charged by minus sign, so the electrons should move from somewhere, and this is the place from which the electrons are flowing to the left, to the right, okay, and then this remains plus, and then this will be minus because it's connected to the minus side. So the current is really flowing here and here, but not there, but just the charges are moving from one side to the other side, because physically the current cannot move between the plates of this capacitor because it's empty space. So in this question, they are solving what is the time constant, what is the equivalent capacitance, and what is the equivalent resistance if you are looking from AB, point AB. In other words, what does the power supply C R equivalent and C equivalent? Also, another part of the question is that when this current drops down to 1.5 milliamperes. So we would like to find this thing. Okay. So first of all, we know that if you look from this side, we have two resistances in series and two capacitors in series. So for resistances, we have to do just add. So R equivalent is just the summation of these two resistances because they are in series. So 2.2 plus 2.2 gives you 4.4 K for the equivalent resistance. But for the capacitors, because they are connected in series, you have to get the equivalent capacitor by just multiplying 6 by 6 and adding them up, right? This is how you do it shortly. It's just 36 divided by 12, and then this gives you just 3 microfarad. Actually, we should have done this quicker, because if two same capacitors are connected in series, the resulting capacitance is just the half of it. So it's just 3 microfarad. Okay, so we found the equivalent capacitor and also equivalent resistance. So these are the resistance and capacitance that the power supply sees, okay? So if we have now this power supply, okay, minus plus, now we have R equivalent and C equivalent. So this is R equivalent and C equivalent. In this case, okay, in this case, we know that the time constants are just simply multiplication of these two. So tau equals just R equivalent times C equivalent. So when we multiply these two numbers, 4.4 K, which is 10 to the 3, okay, don't forget, this is important, times 3 times microfarad, 3 times 10 to the minus 6. So it just cancels this, and then you will end up with 10 to the minus 3, which happens to be milli, okay? So now tau is just 13.2 milliseconds. So this is the reason that they gave this ampere value to find the time. So it will be probably within milliseconds. I don't know how much, maybe a few times of this milliseconds. We will see that. We will see that. Okay. If we want to get steady state value so that there is no more current passing through, in this case, we know that the time which is required will be a few milliseconds, a few 13 milliseconds. But here, they just say, what will be the current value in the initial 1.5 milliamperes. So it must be a value which is near to the equilibrium value. So at t equals 0, what is the current we have to find? So don't forget, this is very important. At t equals 0, because the capacitor plates are so empty, they can allow any kind of charge so that you can treat as short circuit. So treat capacitors as short. Okay. So when they are short at t equals 0, this is the circuit we have now. So just don't hesitate to draw this circuit. So as you see, this is the one of the capacitor which is short circuited, and this is the other one which is short circuited. All we have is just two resistances which are connected in series. Okay, so this is really what happened in the beginning. So at t equals 0, we have this case. So from this, of course, the current will flow, and then it will be named as I0. Don't forget, at t equals 0, the capacitance should be short circuited. Okay, in this case, we have now 12 volts is equal to I0 times R equivalent, which is just 4.4 K. From this, I0 can be found as 2.73 milliamperes. So this is the beginning current which will drop eventually. So the biggest amount of current is just 2.73 milliamperes, and it will start dropping. How is it going to drop? Okay, we know that I equals I0 e to the minus t over tau. So this is a simple circuit, and we know the current will flow exponentially, and for tau we have to use 13.2 milliseconds, and then I0 is this, and this is the current. So this is the current value. Okay, so now what's going to happen is that this current starting from 2.73 milliamperes, suppose the unit is milliampere here, and then this is like milliseconds now, okay? So it will start dropping, and then it will really, okay, get closer to 0 eventually. But what they ask you in the second part of the question, at what time the current goes down to 1.5 milliamperes. So since this is almost 3, it's right there. So this is 1.5, and then what are they asking is this time. So what is this T star? So what is that? At what time the current reduces down to 1.5? So this is what we have to do. So we can use this equation now. They say that I is just 1.5 milliamperes when, of course, I0 we found 2.73 times e to the, okay, minus t divided by tau, which is just 13.2. As you see, this is t over tau. I didn't put millisecond. I didn't put 10 to the minus 3 there, because the time that we will find will be in milliseconds then, okay, dimensionally. Here also I didn't put any milliamperes, because 10 to the minus 3s are cancelled from both sides. So basically, you can solve this simple equation for t. But to do this, what you do is that you put this exponential term to the left and this to the right by dividing, so that you will have e to the t over 13 over 2 will be equal to 2.73 divided by 1.5. So now e to the minus turned out to be e to the plus. Okay, so now at this stage, because of the properties of the exponentials, okay, what you do is that you just simply take the log of both sides. Okay, when we take log of both sides, actually ln of both sides, ln e will give you 1, so you will have t over 13 over 2 on the left, but the right hand side will be just ln 2.73 divided by 1.5. So from this, actually this t is t star. Don't forget, as soon as you put 1.5, you have to put t star there. But this is general expression. So this t star we are solving. So everywhere you have to put t star, and then from this you see that t star is nothing but equal to 13.2 times ln. Okay, 2.73 divided by 1.5. So if you get these numerical values, you find that t star is just 7.9 milliseconds. So it means that at 7.9 milliseconds, current dropped to 1.5 milliamperes starting from 2.73 milliamperes. So this is the solution. So don't forget, when you have this kind of combination, a few resistors and a few capacitors, to get the equivalent resistance and equivalent capacitors, you have to be careful by connecting the parallel, not the parallel, but serial connection, okay, for the capacitors, and the serial connection for the resistances. It's just the sum of the two, but for these two, it's just the inverses are added and, okay, it's reversed. So this is the expression for the equivalent capacitance. So after you find that, you get equivalent capacitor and R equivalent and C equivalents multiplying, you get the time constant. From this, you can just insert in this equation, okay, to get the current as a function of time. It's exponential decaying function, so this is it. And from this, you can find anything, okay.